All right, today we're going to pull back the curtain on the single most important piece of software running on your computer, your tablet, even your phone. I mean, it's the one you use every single second, but you probably never really think about it. I'm talking about the operating system.
So let me just ask you this. What do you think is the most critical program running on your device right now? I mean, is it your web browser, your favorite game, maybe that work software you have open? Well, the answer, it might actually surprise you.
Yeah, because the most important program, it's the one you never even see. It's the one working silently in the background, you know? It's the invisible foundation that makes literally everything else possible. So, okay, let's dive into this and figure out what it actually does.
You know, to really get why we even need an operating system, you got to go back in time a bit to what was basically digital chaos. Seriously, just imagine a world where every single app had to be a master of everything.
So without an OS, every app would have to know exactly how to talk to your specific CPU, your specific memory chips, your particular hard drive. I mean, it would be a total nightmare. Apps would be constantly fighting over resources, right? One app could just decide to hog all the hardware, and a single crash, bam, the whole system goes down. The OS is what steps in. It's the manager, the boss that creates order, protects the hardware, and basically makes sure everyone plays nicely.
So, to put it simply, the OS is the master software. It manages all the computer's resources. Think of it like a bridge between you and all that complex hardware, creating this stable, reliable environment where your other programs can, actually run.
I like to think of the OS as the conductor of a huge orchestra. You've got all these different hardware components, the CPU, the memory, the storage. They're all different instruments, and they all need to work together in perfect harmony. Well, that's the OS's job.
So the OS has a few really key duties. First, it's a resource manager. It decides who gets the CPU and for how long. It also provides the user interface, the pretty graphical one we're all used to, or for some of us, a command line. And super critically, it provides something called abstraction and isolation. And I really want to focus on that idea of abstraction for a second.
Okay, so abstraction. It's basically the OS's biggest magic trick. Think about it. When your word processor saves a document, it doesn't need to know anything about the insane physics of magnetic disks or flash memory chips. Nope, it just says, hey OS, save this file for me. And the OS handles all the messy, complicated details. This one concept is what makes programming and just using a computer in general so much simpler.
But of course, just managing the hardware wasn't enough. We humans are kind of greedy, right? We wanted to do more than one thing at a time. And this demand, it forced the OS to evolve from being a simple manager into, a master juggler.
I mean, this evolution started way back with systems like MS-DOS, which, if you remember, could only do one thing at a time. Then we got batch processing, which was just running jobs one after another. But the first big leap was something called multiprogramming. This is where the CPU would cleverly switch to another task while one was waiting for, say, you to type something. And that eventually evolved into the true multitasking we know today, where the OS slices up CPU time so finely it feels like everything is running at the exact same time.
And believe it or not, the juggling act gets even more complex. See, multitasking, that's like juggling different applications, your browser and your music player, for example. But then you have multi-threading, which is like juggling multiple tasks inside a single application. A perfect example is all the different tabs you have open in your browser right now. And because all those threads share the same memory, switching between them is incredibly fast.
The secret sauce that makes all of this possible? It's a process called context switching. What the OS does is it freezes one process, saving its exact state, and then instantly loads the state of another one. It does this thousands and thousands of times per second. So that seamless flip you do between your email and your music, yep, that's your OS performing a lightning-fast context switch.
Okay, but this wonderful new world of multitasking, it created a whole new set of headaches. I mean, when you have dozens of programs and hundreds of threads all running at once, how in the world do you stop them from stepping on each other's toes?
Well, this leads to a classic computer science problem called a race condition. Just imagine two people trying to edit the exact same sentence in a Google Doc at the exact same time. The final result is going to be unpredictable and almost certainly garbage, right? The very same thing can happen with software threads, and that can lead to corrupted data and system crashes. So the OS has to step in and act as a referee. And it has some cool tools to do this. It uses things like mutex locks, which are basically like putting a digital do not disturb sign on a piece of data. That ensures only one thread can touch it at a time. It also uses other tools like semaphores and guarantees certain operations are atomic, meaning they either happen completely, all at once, or not at all. No interruptions allowed.
Now, the absolute heart of the OS, the part that's doing all this refereeing and managing, is called the kernel. And there are different philosophies for building one. You have monolithic kernels, like in Linux, which put everything into one big, fast package. Then there are microkernels, which keep the core super tiny for better reliability. And finally, you have hybrid kernels, which you'll find in Windows and macOS, that try to get the best of both worlds.
Another really core aspect of any modern OS is its architecture, and I'm sure you've heard of 32-bit versus 64-bit. So what's the deal? Well, the key difference really comes down to memory. A 32-bit OS can only manage about 4 gigabytes of RAM. A 64-bit OS, on the other hand, well, it can handle a lot more.
How much more? A 64-bit system can theoretically address 16 exabytes of memory. An exabyte, that is 16 billion gigabytes. It's a number so vast that for our current needs, it's practically infinite. And this massive leap is what enables the powerful games, the 4K video editors, and the huge data analysis that we all rely on today.
Okay, so we've seen how the OS solves these massive problems of chaos, juggling, and sharing, but how does this all actually come together in your daily life? Well, let's look at the very first thing your computer does when you turn it on.
The moment you press that power button, a whole chain reaction kicks off. First, something called the BIOS, or UEFI, which is kind of like permanent software that wakes up your hardware, does a quick check of everything. Its main job is to find and load a tiny program called a bootloader. And that bootloader has one single mission in life, to load the kernel, the heart of the OS, into memory. The kernel then wakes up everything else. So yeah, the OS is literally the first software to run and the very last to shut down.
So, when you really think about it, the operating system is the unsung, unseen hero of your entire digital world. It's the master manager, the expert juggler, and the tireless referee that makes everything you do on a computer possible. It performs billions of operations a second, all without you ever noticing.
And all this leaves us with a pretty fascinating question for the future, right? As we move towards a world of IoT devices, smarter AI, and globally connected systems, well, the challenges of management, security, and efficiency are only going to get bigger. So what do you think the next great juggling act for our operating systems will be?